Well, we have now seen the fundamental theorem, or at least you should have seen it up to this point. And today we're going to kind of look at the geometric properties of the definite integral, see what it means, and maybe give you a little bit of a shortcut on how to work some of the maybe a little bit more unusual functions. But we'll go through the definite integral process, the fundamental theorem process for this next unique function, the absolute value of x minus 3, and I just realized I did not put all of the function in there that it needed to be. So, well, let's cross that out for now. It should be the absolute value of x minus 3 and then minus 4 on the outside, then dx. Here I try to use all my technology and I mess up. But well, thanks for forgiving me. Well, to be able to do this, we've got to change the form of the absolute value by using the definition of the absolute value. And we'll actually be splitting this up into two different parts. And I think we've mentioned this before, but the absolute value of x is defined as, well, simply x if x is greater than or equal to 0, or if x is negative, then we represent the absolute value of that negative number as the opposite of x. Most of us look at this and say negative x, but technically it's the opposite. Opposite of a negative number is a positive number. So either way, the results of the absolute value will be a positive number, or at the very least equal to 0 in this case. So what we have to do is change the form of this function based on the definition of the absolute value. Now, in this function we said x was on the inside, and we've got to think in terms of the inside. If the inside is greater than or equal to 0, then the result is exactly what is in the inside. Okay. So when we put x minus 3 inside the absolute value, the top value will be x minus 3 if x is what? Okay, greater than or equal to 3. And then how do we represent the bottom part? If
it'll be x plus 3.
Almost.
Negative x minus 3.
Okay, we've got to think the opposite, or negative, and then the quantity of x minus 3. We've got to watch how we say that. We need the parentheses in there, and then this would be for x being less than 3. So another way to write that then, we could say negative x plus 3 on the bottom part. Now, that would be it if we were just looking at the absolute value. But we also have this minus 4 outside the absolute value. So our function then, well, each part we've got to subtract 4 from, and we would get, let's see, x minus 7 and negative x minus 1, right? And again, that's going to be for x is greater than or equal to 3 and for x being less than 3. So our integral starts at 0 and goes to 6. Well, that's going to be split up into two different parts here. Okay. We could say from 0 to 3, we're going to be working with what function? Okay, these are the values that are less than 3, so negative x minus 1. So that would be the first part. And then we add the second part to it from 3 on up to 6. And that's going to be true for x being greater than or equal to 3. So we would integrate x minus 7 from 3 to 6. So because of the definition of this function, we have to go through that first before we can get it into a form that now we can use the fundamental theorem. Okay, the fundamental theorem says all we need to find is the antiderivative of the function and then plug in our integration limits. So this first part, we would get what? Okay, negative 1 times x, antiderivative of x would be our x squared over 2, but don't lose the negative out in front. And then antiderivative of 1, just x. Now, we again have to break this into the two different parts. This antiderivative goes from 0 to 3. And then the next antiderivative, using the fundamental theorem, will go from 3 to 6. This time we'll have a positive x squared over 2 minus 7x. And now, fundamental theorem says we start with this one and then subtract this. So negative 3 squared over 2. Now, remember, this is the negative of the fraction, the opposite of the fraction, not negative 3 squared. It's 3 squared, then take the opposite. So that value will end up being negative, and then minus 3. This would be our capital F of 3 minus, well, capital F of 0, plug 0 in, and what do we get? Most of the time we get 0, but there are occasions where plug 0 in and we get some other number. You got to be very careful with that. Don't just assume 0 here. We always get a 0. Okay. So then plus 6 squared over 2 minus 7 times 6 would be f of 6 for the second part. Then minus the quantity. Be very careful with your subtractions. 3 squared over 2 minus 7 times 3. And doing all the calculations here.
Why did you do minus 3, minus 7, 3 on the second part?
So some calculations here. Negative 9/2 minus 3 plus, well, 36 divided by 2 is 18, minus 42, minus 9/2, and then once again be careful with those little dashed lines. Minus the negative would give us plus 21, and ultimately we end up with what? So simplifying real quickly, those two together will be negative 9 minus 3 and minus 42, get all the negatives together, and then that would give us 39 that we're adding. So that would be negative 3 minus another 3 minus 9 would give us negative 15. Am I correct there? We calculate by committee in here, make sure we're all doing things right. So we get a value of negative 15. Now, this is a value, and the operation ends up giving us a negative answer. That is correct. That is okay for a definite integral to end up being a negative answer. But we're going to be looking at a lot of applications of the definite integral that should end up giving us a positive answer.
Because this is looking for the area, right? And you can't have negative area.
Correct. We're going to be looking at the definite integral to represent area of something, and area cannot be a negative number. But the definite integral can end up being a negative number. Now, let's look at the graph of this function to see how, even with the negative 15, how that represents the area of something. Let's go ahead and graph this function. And the absolute value, do you remember what the graph of that's going to look like? Okay, a V shape. And technically, I don't know that we call it a vertex, but where is the point? Where would the vertex be? Okay, to the right 3 and then down 4. So 1, 2, 3. Negative 4 would be the corner point where the V goes through. And let's see. To give us a little more accuracy on the graph, we will be looking at this from 0 to 6. So we do need to see at least where 0 is and where 6 is. If x is 0, y is going to be what? Okay, negative 1. And if x is 6, y is going to be negative 1 as well. Now, it doesn't have to be that. I picked out kind of a symmetric definite integral here. But we would have the V shape, okay, from 0 to 6. This would be the graph representing that integral. Now, this value we said ended up being negative 15. The definite integral is going to represent area. If the definite integral is positive, it's actually the area under the curve and above the x-axis. But in this case, we get a negative value, which means the area we're representing is below the x-axis. Take a look at the area from 0 out to 6. This area right here, well, we can kind of break it into two parts. It's really a rectangle and a triangle. The area of the rectangle would be what? Length of 6, width of 1. And then the area of that triangle is what? 1/2 base, which is your 6, times your height. What's the height of this? Okay, the height is actually just 3. So 1/2 of 6 is 3 times another 3 is 9. Add these two together. The area of that figure below the x-axis is 15. Not a coincidence that we ended up with negative 15 here. Any area below the x-axis would represent a negative value for the definite integral. Any area above the x-axis would be a positive value. Okay? So the geometric representation here, we are now going to be able to integrate, find the definite integral value for functions that are not necessarily given as a formula. For instance, let's take a look at this graph. We'll call this graph y equals f of x. And let's integrate, let's find the definite integral from -1 to 4. Even though we don't have the formula, we can do this because of the area representation. So from -1, clear out to 4. Now we could have went from 0 to 3 or from 1 to 2. Just look at the area from the left integral limit to the right integral limit. Okay. Now we're going to need to break this into parts from -1 to 0. We have negative function values. So the area we're dealing with there would be below the x-axis, which means that part would end up being what type of value? Okay, now it will represent a negative value. What is the area for the -1 to 0?
1/2.
Okay, correct. It'd be 1/2.
Or -1/2, yeah.
So we'll say area, this first one is 1/2, but as we use it to evaluate the function, we'll have to say -1/2 to evaluate the definite integral. Okay. Then area of our second part, well, we may need to do a little more here. Looks like it goes from 0 to about 2.5. And what kind of area do we get there? This would be 1/2, this would be 1. What about this one? To find what this area is, well, we have a height of 1. The base would be what?
I think it is half because once you go down here, it goes up.
Okay, right. The slope of that line, okay, go down 2 and over 1. So we go down 1 and over 1/2. There's many, many different ways to show, but this will be at 2.5,
But then the other
based
one
on the slope.
is at 2/3 or 1/3?
Okay.
It's 1/3.
Yeah, we'll have to kind of take a look at that one. It's not nearly as straightforward, but okay. So from 0 to 2.5, or at least, what's the area of this triangle?
1/4.
Okay, 1/4 is going to be 1/2 times the base, which is 1/2, times the height, which is 1. So the area of the second part from 0 to 2 will be 1 3/4. The area of the third part, we may need to break this down even further.
Why did that logic of the slope work? I just feel like that's right.
This part from 2.5 to 3, I guess we'll call that 2.5 to 3 would be another 1/4. Okay, same idea as this one up here. Okay, we better put in our numbers. This 1 3/4 was above the x-axis, so For the definite integral, that would represent a positive value. But then area of our third area being below the x-axis, we'd have to say negative 1/4. And let's see, we need to find what this value is. Right, the slope of this line, 1, 2, 3, and over 1. Up 3 and over 1. So if we only go up 1, we would have to go over 1/3. So the base of this triangle would be 1/3. So we'll call that area 4. 1/2 times the base of 1/3 times, okay, height of 1. Area of that triangle will be 1/6. But again, it's below the x-axis, so in terms of our definite integral, minus 1/6. And then finally, our last part here, this is above the x-axis, so definite integral would be a positive value for that part. Area of that one, 1/2 times, well, the base in this case would be 2/3. And then the height, well, the height of that one will be 2. So the area of this triangle ends up being 2/3. So add and subtract. I guess we're adding negative numbers. So the result, this particular definite integral based on the graph of this function will equal what? So quick calculations with some fractions. Common denominator of 12, numerator, well, 21 minus 6 minus 3 minus 2 would be minus 11. So 10, and then plus 8, 18 over 12, or 1 and, well, 6/12, 1 and 1/2. That would be the value of this definite integral based on the function using this graph. Questions? So now you know how to integrate not only using the fundamental theorem, but also using the geometry, looking at the area either under the curve or above the curve to calculate the definite integral value.
So when you take, like,
Had this value ended up being negative, all that would mean is there's more area under the x-axis than there is above the x-axis. But in this case, there's a little bit more above the x-axis than below the x-axis, which, yeah, looks like it would be. But that will be a geometric way, sometimes a shortcut. If you recognize the graph of the function, then you can use the area formulas rather than going through the integration.